Hello, and thanks for using TickBoom. For this question, a student has asked to prove that for integral AB, that a cubed minus b cubed is even if and only if a minus b is even. And I think there's probably a few ways you could try and tackle this. Often with proofs, there's always more than one way to skin the cat. But the approach I want to take is really quite a simple, basic, first principles way of tackling this. So it's definitely not going to be the most elegant or beautiful proof out there. But I think if you're the type of person who struggles with working out those kind of creative and imaginative proofs, then you might like this approach, because it really just does start from first principles and kind of just takes a brute force approach to it. So I'll just write out what we're being asked to show. So we need to prove that a cubed minus b cubed is even if and only if a minus b is even. And that if and only if, what that means is it won't be enough to just show that if a minus b is even, then a cubed minus b cubed is even. That's necessary. But over and above that, we also have to show that if a minus b is not even, in other words, it's odd, then a cubed minus b cubed will also not be even. You need to show all of that. And so, really, I think that we can take a case approach to this, and we can define four possible cases that we can investigate and see where we get to. And I think they are: A could be even, and B could be even. That's one possibility. We could have A could be even, and B could be odd. We could have A as odd, and B as even. And then we could have A as odd, and B as odd. And hopefully you see that this covers all the possibilities. Given we're dealing with two, an A and a B, just two items here, these four cases are mutually exclusive and exhaustive. They cover all the possibilities. So if we can work through each case one at a time and see whether A minus B is even and A cubed minus B cubed is even or odd, then we hopefully can make the conclusion that we're being asked to make. So let's just do it. Let's just work through each case one at a time. So for case one, if we want A even and B even, we can let A equal 2n and B equal to m, and that's where n and m are some integers. So this is a classic way of defining an even number. So now if we go a cubed minus b cubed would be 2n cubed minus 2m cubed. So that's 8n cubed minus 8m cubed, which can be written as 4n cubed minus 4m cubed. So I can conclude that that's even, because it's 2 times some integer. Since if n and m are integers, then 4n cubed and 4m cubed will also be integers. Now if I just look at a minus b, that will be 2n minus 2m, which will be 2n minus m, so that's also even. So that's a good start. When a minus b is even, in this case we also get a cubed minus b cubed being even. So now let's look at case 2. So a is even, b is odd, so we'll let a equal 2n, just like before. But this time for b, we'll let that be 2m plus 1, because that's a common way to define an odd number. Take an even number and add 1. You could also take an even number and subtract 1. That's another way to think about an odd number. So again, we can look at a cubed minus b cubed, which would be 2n cubed minus 2m plus 1 cubed, which is 8n cubed minus Here I'll just call this 2m plus 1, 2m plus 1 squared, and then I'll expand. So we'll get 8n cubed minus 2m plus 1, then we'll go first one squared, plus twice the product, plus the last one squared. So that's 8n cubed minus, now I'll expand this, so we'll go 8m cubed plus 8m squared plus 2m plus 4m squared plus 4m plus 1. So that's going to be 8n cubed minus 8m cubed plus 12m squared plus 6m plus 1. I might just turn over at this point. So we're still looking at the a cubed minus b cubed, and we've got 8n cubed minus 8m cubed minus 12m squared minus 6m minus 1. And I can write that as 4n cubed minus 4m cubed minus 6m squared minus 3m, close bracket, minus 1. And I can conclude that's odd because I've got an even number, minus 1. So now if I look at a minus b, that's going to be 2n minus 2m plus 1. So 2n minus 2m plus 1, which equals 2n minus 2m minus 1. We can write that as 2n minus m minus 1, so I can conclude that's odd. So here we had a minus b not being even, and we also had a cubed minus b cubed not being even either. So also a good sign. Now we'll go to case 3. A is odd, b is even. So we let a equal 2n plus 1 and b equal 2m. Now hopefully you'll see that we're just going to get the same as case 2. I'll work through it just for completeness, but hopefully it should be no surprise that we're going to get the same outcomes. So if I did a cubed minus b cubed, I'd get 2n plus 1 cubed minus 2m cubed. This 2n plus 1 cubed will just be the same as what I got with 2m plus 1 cubed, just with n's instead of m's. So we'll get 8n cubed plus 12n cubed, plus 12n squared plus 6n plus 1 minus 8m cubed. So I can write that as 4n cubed plus 6n squared plus 3n minus 4m cubed, all plus 1. So we see here we also get an odd result because we've got an even number plus 1. So hopefully that makes sense. Now a minus b will be 2n plus 1 minus 2m, which I can write as 2n minus m plus 1, also odd. So as I explained, we get the same result as case 2. They're basically the same thing. Now if we look at case 4, and that's where a and b are both odd, so we'll let a equal 2n plus 1 and b equal 2m plus 1. So a cubed minus b cubed will be 2n plus 1 cubed minus 2m plus 1 cubed, which will be, can take our result from before, 8n cubed plus 12n squared plus 6n plus 1 minus, and here it'll just be an m instead, so 8m cubed plus 12m squared plus 6m plus 1. And I'll just expand this minus. So 8n cubed plus 12n squared plus 6n plus 1 minus 8m cubed minus 12m squared minus 6m minus 1. The plus 1 and the minus 1 cancel, so we can write this as 2 4n cubed plus 6n squared plus 3n minus 4m cubed minus 6m squared minus 3m. And that's even because it's 2 times an integer. Now I'll just turn over. If we look at a minus b, that will be 2n plus 1 minus 2m plus 1, which will be 2n plus 1 minus 2m minus 1. Plus and minus 1 cancel, we get 2n minus m, and we can conclude that's even. So now, if we look now that we've worked through our 4 cases, we see when a minus b is even, a cubed minus b cubed is even, and that happened in case 1 and case 4. And when a cubed minus b cubed was not even, when a minus b was not even, a cubed minus b cubed was also not even, and that was in case 2 and 3. So in terms of our conclusion, we can conclude that in all possible cases, a cubed minus b cubed is even if and only if a minus b is even. So that's what we can conclude. So therefore, a cubed minus b cubed is even if and only if a minus b is even. And that's the proof. So hopefully you've been able to follow along with that, because it's really just simple simple algebra. The key to it was thinking of these 4 possible cases and just knowing how to define even and odd numbers. And from there the results come out quite easily without too much complicated math, which is why I think some people might find this proof attractive, because it is so straightforward. It doesn't require any sophisticated techniques. Often when you see a cubed minus b cubed, you might instinctively go to the expansion of that and then see if you can do any other rearrangements to make a proof. But I think this proof actually gets you to where you need to get to, but with very simple techniques. So hopefully you've found that helpful, and tick boom.